So this may be a little small to read. This is from yesterday, but I'll try to write a little bigger. But if you have trouble seeing, please let me know. So let's recall from yesterday. I was looking at this spectral expansion, trying to expand the characteristic function of a set using mass forms, Eisenstein series, and constants. And then we wanted to prove that the inner product of your of this measure y to the k mod f z squared on the mass forms and the Eisenstein series for fixed mass form and a fixed Eisenstein series goes to 0 as k goes to infinity. And we began discussing what happens with the inner product with Eisenstein series. That's kind of an easy calculation. You do the Rankin-Selberg unfolding method, and then you can evaluate what this inner product with Eisenstein series is. It turns out to be something which involves L functions. The numerator is the L function of the symmetric square, L function associated to f at the point half plus it, and you want some upper bound for it. And then the denominator is a little bit more tame. It's just the symmetric square L function evaluated at 1. This, if you like, comes from the way in which we normalize our function f. We normalize it so that its L2 norm is 1, rather than taking the Hecker normalization of setting the first Fourier coefficient equal to 1. Okay, we have this constant c, which was in the Fourier expansion of f. And what I ended with last time was to say that there's something called the convexity bound, which barely fails to give you the result. But if you had something called subconvexity, which beats convexity by a little bit, or if you had the Riemann hypothesis, then you would know that that this inner product goes to 0 as k goes to infinity. This is what happens on the Eisenstein series case. Now, in this approach, we also have to deal with the inner product with mass forms. So that would be the integral Is this big enough? Or should it be bigger? Slightly bigger? Okay. Maybe let me try the Sharpies. Maybe that does work better. Okay, so this is not so easy to evaluate what this integral is, because there's no way in which I can just unfold this function phi. I don't have any nice expression for it. So this is a complicated thing, but it turns out that if you square this integral, this is also related to L functions. So the exact formula is written down in the notes. So it's kind of a complicated thing. There are various things that you have to calculate. What it involves is the L function at half of something called the triple product L function of f times phi j, divided by, again, various gamma factors that I'll forget. And then what you have is L1 sim squared f squared times L1 sim squared phi j. Okay, this should, at least formally, it should, you should think of this as being exactly the analog of the formula that I had for Eisenstein series. So if you square the formula that you see for Eisenstein series, it should look a little bit like this formula. So I'll explain what this triple product L function is, at least a definition of it. Let me just say that, F and phi are GL2 objects, so they have degree 2 Euler products. So when you take the triple product, you should get an Euler product with 8 terms in it. And here, this I defined yesterday. The zeta has an Euler product with 1 factor. The symmetric square has 3 factors, so you get something with 4 factors here. But of course, when you square it, you get 8 factors. So this formula is the exact analog of the formula that we see for Eisenstein series, except that it's much harder to prove. Okay, so this is a formula which is the work of many people. So it started with work of Harris and Kudla. So many, and also Gross Prasad. And the formula in the particular way that I've stated it is due to Tom Watson from about 5-6 years back. Okay, and what is this triple product L function? So F and phi are all Hecker eigenforms. So remember that we wrote lambda f of p as alpha f of p plus beta f of p, where these were of size 1. For the phi j, again, you have these Hecker eigenvalues, which I'm going to write as, well, okay, too many subscripts, so let me just write alpha sub phi of p and beta sub phi of p. Here we don't know the Ramanujan conjecture, so I don't know that these are unimodular, but that's okay. And then what is this triple product? You form all possible combinations of these taken 3 at a time. So one combination would be alpha f of p times alpha f of p times alpha phi of p, and then you have various combinations going up to beta f of p times beta f of p times beta phi of p. Okay, so you have 8 combinations in all. And then you define the triple product L function to be the product over all primes p with these 8 Euler factors. So there are 8 terms here. Okay, so of course, this is it's not obvious that when you take this product that you should get something nice, but there is work of Garrett who showed that this triple product L function has an analytic continuation and functional equation. So there's a functional equation which, the way I've normalized it, would connect S to 1 minus S. So the way I've normalized my Hecker operators always is so that when I write down the L functions, there'll be a functional equation which connects S to 1 minus S instead of S to K minus S or whatever. This is much nicer from the analytic point. So the formula connects the central value of this L function to this triple product square. So it's quite a remarkable formula. For example, one thing it says is that the central value at half is actually non-negative because the left-hand side is clearly non-negative, which is something we expect for all L functions. If they are real valued and you think that the Riemann hypothesis is true, then it better be positive at half or non-negative at half, but it's not something which is easy to prove in most cases. So we're going to take this as a black box. Now I should say, how is this normalized? So I kind of omitted writing down the gamma factors, which are written down in the notes. But the way it's normalized is that the integral, the triple product squared, it's of size, once you work it out, it's basically of size L half of this triple product. In the Eisenstein series case, it was divided by a k, basically, which is a parameter going to square root of k in the Eisenstein series. Now it's something divided by k, as you might expect by taking squares on both sides. And then I have basically L1 sim squared f squared. I'm forgetting the L1 sim squared phi j because, again, I'm thinking of j as being fixed and k goes to infinity, so I don't care what that dependence is. So I'm only interested in this L1 sim squared f. So when I discussed the Eisenstein series, I said that the denominator L1 sim squared f had a lower bound. It was bounded below by 1 over log k, thanks to Hofstein and Lockhart. And we have the same lower bound for the denominator. And now again, we want an upper bound for the numerator. Okay. So we have to work out what this convexity bound in this case is going to be. You can kind of guess what convexity will give you. It'll give you precisely that this numerator is bounded by k. So you get no information out of the convexity bound. And again, subconvexity would give you everything, which is still open. Would now imply decay of this triple product. So in particular, if you assume GRH for these triple product L functions, again, you would know that the inner products with mass forms goes to 0 as k goes to infinity. So I should say that this approach to the problem was something which was initiated by Sarnak very early on in the mid-90s. He knew, of course, that what you get when you take the inner product with Eisenstein series, that's a classical theory. And then at that time, the triple product connection was not very clear, but they began to think that maybe there's a connection for the triple product with some other class of L functions. And that was worked out in these series of papers leading up to Watson. So at some kind of conceptual level, this solves the problem because it tells you why the result should be true. It's true because we believe in the Riemann hypothesis, and the Riemann hypothesis certainly implies what the answer here should be. And even with very nice rates of decay, the Riemann hypothesis would tell you that this numerator is bounded by k to the epsilon. So you get not only that the inner product with mass forms goes to 0, it even goes to 0 like 1 over square root of k. Okay. One other point is that in this approach, I've only talked about what happens if you take the holomorphic case and you take the inner product with mass forms and Eisenstein series. You could do the same arguments for the mass form case. You could take a mass form of large eigenvalue and then compute its inner product with the Eisenstein series, or compute its inner product with fixed mass forms phi j. You would get exactly the same results. You would get in the one case trying to prove subconvexity for symmetric square L functions for mass forms, and then in this case you would get some trying to prove subconvexity for this triple product L functions. By the way, there are cases in which you can prove this subconvexity if you take two forms. So let me just make us a remark. If you fix two forms, say phi1 and phi2, so these are fixed, and then you take the triple product with f, and f is varying, so here the subconvexity problem is known. So this is due to various people, so Bernstein and Reznikov and also Akshay Venkatesh. but somehow this is not what we need. The one that we need is somehow very different from what we can prove. So I'll try to explain maybe next time what the convexity bound is and why in some cases we can succeed and why we can't in other cases, at least briefly. Okay, so now let me say what we can do is I can prove something called weak subconvexity. And maybe I'll discuss this next time. So this is kind of a very general result, but it doesn't save you a power of k. It saves you just a log k, or almost a log k to the 1 minus epsilon. So this holds for L functions satisfying some kind of Ramanujan condition. So I have to explain what this weak Ramanujan is, but for the moment, let's just let's not worry too much about it. So I need something like weak Ramanujan because for this L function f times Pj, the f satisfy Ramanujan, but the Pj need not satisfy Ramanujan. Okay, so I have to think a little bit. I want to include this example, but the Pj is fixed, and that kind of that's enough. So what it proves is that, you know, whatever it means, so for L half of some L function pi, you get something like the convexity bound is always something called the conductor to the 1/4, and I can prove, and you want to save some power of the conductor, but instead of doing that, I can prove this divided by the log of the conductor to the 1 minus epsilon. I'll explain what this conductor is maybe later. Okay. So that means that gives a couple of corollaries. So it shows that if you look at L half plus IT sim squared f, where the convexity bound was square root of k, I could prove here that this was bounded by square root of k divided by log k. And similarly for the triple product L function for L half f times Pj, you can prove that convexity bound was k, and you can prove something like k over log k to the 1 minus epsilon. Okay. So now if you plug this in, you see that the inner product with Eisenstein series so here I would get, so this guy divided by L1 sim squared f, so I would get 1 over L1 sim squared f times log k to the 1 minus epsilon. And then in the inner product with mass forms, so there I had only one triple product L function, so I get again this log k to the 1 minus epsilon, but now I get two copies of the L1 sim squared f. Okay. So this means that if L1 sim squared f is bigger than log k to the minus half plus delta for some delta positive, then we are done in both cases. So actually, if it's bigger than log k to the minus 1 plus delta, then I would know that the correlations with the Eisenstein series goes to 0. And if it's bigger than log k to the minus half plus delta, I need for the correlations with mass forms to go to 0. But all we know is that these guys are bounded below by 1 over log k, which is already a very, very nice and useful result. And we can't expect to get anything more than this. So for example, even for the Riemann zeta function, we don't know that there's a lower bound for the zeta function at 1 plus it, which is better than log t to the minus 2/3. That's the work of Vinogradov. That's related to getting a better zero-free region for the zeta function. So it's very, very hard to improve this power of log. It looks like you're asking for a little bit, but you're actually asking for a lot. You're asking for something much better than the classical zero-free region for zeta and L functions. So this might be a harder problem to do than subconvexity. At least every indication is that this is harder. But again, the Riemann hypothesis would tell you that bounds like this are true. So GRH would say that in fact you're bounded below by 1 over log k. Right? So you would be done at this stage as well. You could assume now GRH, and then again you would have a proof that the things go to 0. But maybe it would have been better to assume it at an earlier stage. So at least you know you have some hope of making this work, but maybe not really. But you can see that I don't need all of subconvexity. If I could get a bound which was square root of k divided by log k to the 2.1, that would be great. That would solve the problem completely. But there's kind of a limit on my method, and I don't see how to get any power of log in the denominator better than 1. So that's the first approach. But fortunately, there's another approach. So which let me recall from yesterday. The other approach was, instead of looking at a spectral expansion for the characteristic function of your set, you expand it using these Eisenstein and Poincaré series. Okay, so and here the problem was to show that the inner product of y to the k mod f z squared with Poincaré series goes to 0 if you fix a m not equal to 0. And then for the case with the incomplete Eisenstein series, you want it to go to some limit. Now, this idea is also an approach of Sarnak. So I think actually of Luo and Sarnak in this case. So once they were stuck with proving subconvexity, they had this alternative idea, which is to compute the inner product with Poincaré series. And the reason you can do it is by the same unfolding principle. So if you take the inner product with, say, with Poincaré series, you have y to the k mod f z squared, and you want to compute the sum over gamma and gamma infinity mod gamma. That was the definition of the Poincaré series. And now again, I just replace everywhere the z by gamma z and use the fact that this is invariant and that's invariant. And then I would get the sum over all gamma and gamma infinity mod gamma. And then sum over all the fundamental domains, and then you get an integral over a fundamental domain for the upper half plane modulo the translations, which is just this nice region of width 1. Okay, so here y goes from 0 to infinity, and x goes from 0 to 1. So I can now use Parseval to evaluate this integral over x. So we use So what would I get? So recall that f had some Fourier expansion, which was some constant times the sum of these Hecker eigenvalues, lambda f of n. The way I normalized it would have an n to the k minus 1 over 2, and then an e to the 2 pi I nz. And I take 2 copies of that and then integrate with respect to e of mx as well. And then what I get is that the integral from 0 to 1 that would give me a c squared, whatever the constant is, a sum over n, and then lambda of n, lambda f n plus m. So you want n and n plus m because of this e of nz, picking up the orthogonality, and then you have something like n to the k minus 1 over 2, n plus m to the k minus 1 over 2 from these, and then something like e to the minus 2 pi 2n plus m y. Or maybe 2n plus 2m. So maybe put a 4. Okay. Whatever it is, you just work out what this relation gives you. So that's something like, so then when I integrate this over y, then I have this integral over y going from 0 to infinity, something here like square root of n times n plus m times y to the k minus 1, and then e to the minus 4 pi n plus m y dy over y. If I did this right. Okay. There was a y to the k over y squared, which I wrote as y to the k minus 1 and dy over y. Right? And you can see that this kind of looks like the gamma function evaluated at k minus 1, because I can make a change of variable replacing 4 pi n plus my by some other variable c. So this, you can make a change of variable, and it reduces to something like square root of n times n plus m. There was also, okay, so I forgot one thing. There was a psi of y, which was here everywhere. Right? There was a psi of y in my expression. So if I make this change of variable, I have something like square root of n times n plus m over 4 pi n plus m to the k minus 1, and then some integral of psi of okay, whatever it is. Okay, so t over 4 pi n plus m, t to the k minus 1, e to the minus t dt over t. Okay. Now, so you have to think a little bit about this integral, but it's not so bad. You just have to think of, when you write down so we are interested in the limit as k goes to infinity, and you want to say, if you write down the definition of the gamma function and you think of k getting large, where will the integral be concentrated? That's an easy enough calculation. You just take this function t to the k minus 1, e to the minus t, you differentiate and see where it takes its maximum. And it'll take its maximum when t is about size k. So what you see is that this integral is dominated by values of size t around k. So what I really have here is an expression which is like psi of k over 4 pi n plus m. So what this amounts to is something like gamma of k minus 1 times the sum over, there's a c squared still, a sum over n, lambda of n, lambda of n plus m bar, these various powers of square root of n, n plus m, etc. These are actually pretty close to 1, as you can see. Minus 1. And basically what you have is the function psi evaluated at k minus 1 divided by 4 pi n plus m. What does this mean? So you have to also figure out what c squared is, but that's an easy calculation from Rankin-Selberg. If you think of psi was just some compactly supported smooth function on the real axis, so maybe you think of psi as being some function supported on 1 to 2, let's say. So then what I'm picking up are those values of n which are pretty close to k. So n is basically, so what you have is a sum over n, which is basically of size k. Maybe it goes from k over 2 to k, or k to 2k, or something like that. And then what I have is essentially this Hecke eigenvalue at n multiplied by the Hecke eigenvalue at n plus m. And the way the normalizations will work, I'm summing over k terms here, so I'll be kind of dividing by a k. So the c squared would have a 1 over gamma of k in it, so that's where this extra k will come from. And then there will be, when you compute what the normalization is to make your L2 norm 1, you would get the same object that we've seen before, L1 of sim squared f. Okay, so this is I've kind of basically given you how this calculation goes. It's not a very hard thing. You can just, this is what you get. So the problem now is to show that this goes to 0 as k goes to infinity. And throughout we are thinking of m as being a fixed non-zero number. Now, okay. Now there's also the case when k equals 0, when m equals 0, which is the inner product with Eisenstein series. You can carry out exactly the same calculation. What you get in that case, well, you get exactly the same thing. You want the inner product with, you want lambda of n with lambda of n conjugate. So you want to understand the sum over n about size k of the size of lambda of n squared, again normalized by k times L1 sim squared f. And then you want that this should go to some constant. So it'll be 3 over pi times whatever these normalizing constants would be. Now this statement, at least you should find something which is reasonable. You can recall, if you think of Rankin-Selberg theory, it precisely allows you to calculate something like the sum over n up to x, the sum of the squares of the Hecke eigenvalues when x is large, and if you fix a form f. And you would get that this would be asymptotic to some constant to x times something like the residue of the Rankin-Selberg L function at s equals 1. By the standard technique, you write down the generating series, you figure out where its first pole is, and you compute the residue. The first pole will be at 1, and then you get this residue. And this residue we know is exactly L1 sim squared f. So this is kind of a very reasonable statement that you should have this asymptotic. But of course, when we do Rankin-Selberg, we are kind of interested in figuring out what happens when we fix a form f and you let x go to infinity. And now we have something more complicated where the form f has large weight k, and n doesn't go really up to infinity, it goes up to k, so this is kind of a more delicate problem. So again, you would, as you might guess, what you could prove with kind of convexity is that this kind of formula is true if x is bigger than k to the 1 plus epsilon. And if you had subconvexity for the same symmetric square L function, you would get that the asymptotic formula would hold if k is bigger than 1 minus, x is bigger than k to the 1 minus epsilon for some epsilon. So this looks like we're kind of going round and round in circles, because again, subconvexity would allow you to solve, at least in the case of the inner product with Eisenstein series, with incomplete Eisenstein series, it would allow you to show that the asymptotic holds. Okay, so here, so Luo and Sarnak made this reduction. They reduced the problem of showing QE to establishing this asymptotic formula for m equals 0, and for saying that this the shifted convolution problem has cancellation when m is not equal to 0. I should say in this case also, suppose you take something like the coefficients of the Ramanujan delta function. So you have tau n plus 1 for in the simplest case, and you study that as n goes as you sum over n goes up to x goes to infinity. We know that there's cancellation in that. The tau n should have signs which are plus minus, tau n plus 1 will have signs which are plus minus, and they should know nothing about each other. And when you multiply them together, they will cancel out randomly. So if you again think of this problem as n up to x going to infinity, we know there's cancellation in this, but the delicate point is that you're not letting x go to infinity. X grows like k, which is related to the conductor of f. So this uniformity is kind of a crucial issue. So this is the problem that is considered by Holowinsky. And he kind of does something very funny. So you want to find cancellation in the shifted convolution problem. And what he decides to do is not to find cancellation in the shifted convolution problem. So he studies, instead of this, he looks just at the size of lambda f n times lambda f n plus n. So it looks like at this stage that you've kind of given up a lot. How would you possibly hope that that this should actually be small? You've forgotten about getting any cancellations at all. And the idea here is that Hecke eigenvalues tend to be small. Okay, so in other words, small means that it's like a small negative power of log, right? Why should one think that something like that is true? So let me give you a kind of a reason why. So let's think of an example, but this has nothing to do with this. This is just for intuition. Suppose I think of the Ramanujan tau function. So actually my tau is going to be not Ramanujan's tau, but divided by n to the 11 over 2. So that my tau is going to, on the primes, is going to lie between -2 and 2. Okay. And I ask you, what is the size of tau n? Okay, so, well, by Rankin-Selberg theory, we can work out what the size of tau n squared is. That's just taking the Rankin-Selberg convolution of delta with delta. You work out what it is. That will be asymptotic to some constant times x. And this c will be the value of the symmetric square L function associated to delta, evaluated at 1. Well, that means that if you use Cauchy's inequality, the size of tau n will be certainly at most the size of tau n squared times summing 1 up to x, so x to the 1/2. Okay. So certainly this is bounded by, so this constant c, actually c to the half times x. Okay, but we know that in Cauchy's inequality is tight only if the tau n are all of the same size. Right? Otherwise, we expect to save something over Cauchy's inequality. But we don't expect tau n to be close to 1, because if you look at the tau p's, these lie between -2 and 2, and we expect that these are distributed according to something called the Sartor-Tate distribution. Which we actually know in this case. We know that for the delta function now that Sartor-Tate is true. But that means that there will be some value, there will be lots of primes p for which tau p is pretty big, like 1.5, say. Okay. Now, if you multiply a bunch of those guys together, then you will produce lots of values of tau n which are bigger than some power of log. So in other words, the fact that these tau p's are distributed according to Sartor-Tate means that there's considerable fluctuation a lot in size. And now you can understand that if it takes large values and small values and then you compute the mean square of it, the mean square is going to amplify the large values. So if you know that the mean square is only of size x, you would expect that the L1 norm, just summing the tau n's in absolute value, that's going to be a little bit smaller than x. Okay, and you can make this precise. So this suggests, and you can prove, you can also prove this without using Sartor-Tate, so which is good. It was done in the mid-80s before Sartor-Tate. You can prove that the sum of tau n up to x is bounded by x divided by some power of log, like log x to the 1/18. Okay, some small power of log. You can improve this power of log if you assume Sartor-Tate. Okay, so that's kind of the point. The point is that on average, these numbers, lambda fn, this is not a proof, of course, because here I'm fixing my function and letting x go to infinity. Again, I'm not fixing anything and n goes only up to k. So, and Sartor-Tate is not useful here because it's not a uniform thing. It's not achieved so early on, or we have no way of proving that. But nevertheless, you might think that these numbers are smaller than 1 on average, and then when I multiply two of them together, and these are n and n plus 1 are more or less independent. There's no prime that divides n, which is going to appear in the factorization of n plus 1. And the same thing for, if you take n and n plus m for any small value of m, their multiplicative structures are going to look very different from each other. So you have to kind of prove a couple of things. So one thing is to show that the average value of the sum of lambda f n plus 1 or n plus m it's kind of independent, so it kind of behaves. This is not a rigorous statement at all, that it behaves like the product of these averages. Okay. So, and here there is actually a beautiful theorem of Nair, which allows you to say something like this, except that instead of saying that they're actually close to each other, it gives you an upper bound that this is more or less true. And then if you expect that these guys are small on average, then you can plug that in, and that gives you a way of bounding these shifted convolution sums. Okay. So that's what he does, and what he finds is that this inner product, so the inner product with Poincare series, shift the convolution problem, I put in this L1 sim squared f. It's going to be bounded by L1 sim squared f times something like the product over the primes up to k of 1 plus mod lambda f p over p squared times 1 minus 1 over p squared. Okay, so maybe if I have time, I'll try to explain what this actually means. You can think of this as kind of some naive expectation of what you might expect this sum to look like, this average to look like. If you play around with that a little bit, then what you get is that this is bounded by something over the primes up to k, and what you get is minus something like lambda fp minus 1 squared over p. I think that's right, but if it's not right, believe whatever it is in the notes, not what I say here. Okay, so now you can see this is quite nice because at least this is always less than 1 in size, right? So if I want to show that this is going to 0, all I need, so all that we need in Holowinsky's approach is that the size of the lambda fp's is not too close to 1 for some number of primes. Well, I mean, I need it to be not so close to 1 for a lot of primes, for which the sum of 1 over p being large. Okay, if I can arrange that, then that's done. Now, well, so if lambda f p is close to 1, then that's kind of saying that lambda f of p squared is close to 1. Okay, but this is the same as saying that lambda f of p squared plus 1 by the Hecker relations. So that's close to 1. So we have a problem with Holowinsky's approach only if lambda f of p squared is close to 0 for many small primes p. If that happens, then we have a problem with Holowinsky's approach. But if this happens, then you can look at the symmetric square L function L1 sim squared f. What it really is, it's essentially of size the sum over p up to k of lambda f of p squared over p. You just write down the Euler product defining this and pretend that you can take the Euler product up to size k and that everything else is kind of negligible. You can actually justify this. The key step is to note that there's no Siegel zero for this function, which we know thanks to Hofstein-Lockhart. So you have some expression for the value of L1 sim squared f, and now suppose you're in the situation where Holowinsky's proof fails. So the lambda f p squares are all close to 0. Well, okay, so you plug that in here, and then you see that if this is true, then the size of the symmetric square L function has to be of size 1. If it is anything different, then you're done by Holowinsky's approach. But now if you look back to what we had with weak subconvexity, so there I said that if the size of L1 sim squared f is bigger than log k to the minus half plus delta, then that method works. So now you can see this method fails only if the symmetric square L function is of constant size, but if it's of constant size, I'm already done by the other method. So if you put the two things together, then you're done. That's what happens on the incomplete Poincare series. On the incomplete Eisenstein series, you actually need one more trick. So Holowinsky has so I won't give so many details of this, but the argument is a little bit more complicated. He has a beautiful argument which is probably useful in many other contexts. So just a rough idea of that argument. Instead of integrating the inner product of your Eisenstein series over a fundamental domain, imagine that you bring your fundamental domain down to something like 1 over y so to some Siegel domain like this. This is x goes between minus half and half, or 0 and 1, and y is all the points lying above 1 over y. Okay? And you integrate on this region fy of this is kind of a nice, you can do this integral because this is a nice region. It just splits into the integral from y, x goes from 0 to 1, y goes from 1 over y to infinity. So you can use Parseval to evaluate terms in this integral nicely. But also geometrically, this is quite nice because I have my fundamental domain, which is kind of sitting out here. That has volume, some constant pi over 3. What is the volume of this region? Well, there's a lot of the hyperbolic plane way down. So the area of this region is something like y. Okay, so this makes it believable that what this region really is that it contains something like y copies of your fundamental domain. And you can check that geometrically. It's approximately, this integral will be y times, maybe I should put a 3 over pi or something like that, or pi over 3, copies of the full integral over a fundamental domain of this quantity. And so doing this calculation gives you a slight flexibility. Instead of wanting to know that the sum of lambda fn squared, when you sum it up to n goes up to k, instead of knowing that this sum is converging to the right amount, you have to show only that if you sum it up to k times something, that's converging to ky times L1 sum squared f. And it turns out that if y is a small power of log, you can justify this using weak